So mean arterial pressure is kind of like it says. It's the average pressure in a complete cardiac cycle. That's the way I would remember it. And, to understand this again, we already kind of talked about total peripheral resistance. Remember, they can also, instead of saying TPR, they can say, okay, well, what's the systemic vascular resistance? Remember, these two terms are essentially synonymous. Both approximate to the afterload, right? And when afterload goes up, TPR goes up. Okay, so we already talked about all of that. Again, determined by what structure? The arterioles primarily are going to dictate total peripheral resistance. If we take the total peripheral resistance, we can plug that into our equation with cardiac output to get the mean arterial pressure. Okay, so again, there's lots of different ways you can write this, right? So you remember the mean arterial pressure is equal to the cardiac output times the TPR. And you can also write this as the mean arterial pressure is equal to the stroke volume times the heart rate times the TPR. And we can also write this as N diastolic volume minus N systolic volume times, right, put this in parentheses, times heart rate times TPR. Okay, so there's, like I said, if you kind of work your way up in these equations, all of this can kind of make sense to you. But that's what we're talking about when we're talking about the mean arterial pressure. A lot of this is just derived from the equations that we already went through. But you can see that if you increase the total peripheral resistance, remember I told you that this is essentially going to be in some ways synonymous with the diastolic blood pressure. Okay, so when I increase TPR, I'm primarily increasing the diastolic blood pressure. So the majority of the cardiac cycle is actually spent in diastole. So if we take 2/3, which is approximately how much of the cardiac cycle is spent in diastole, we take 2/3 times the diastolic blood pressure, okay, and then we take about the amount of time that's spent in the systolic phase, 1/3 times that, right? This is just referencing the amount of time that's spent in each phase. We add these together, that will get us the mean pressure. Okay, so that's the concept. And total peripheral resistance is primarily going to be acting here, cardiac output primarily acting, on the systolic blood pressure side of things. Okay, just cleaning things up here. So the pulse pressure is going to be the systolic pressure minus the diastolic pressure. And we can essentially say that if I take the difference in these pressures, that's going to be proportional with how much blood I'm ejecting with each beat. Okay, because I'm taking the pressure that it takes to eject that blood minus essentially the afterload. Okay, so it's essentially, remember, diastolic pressure is kind of like the TPR. And so that difference is going to say, hey, this is how much blood was ejected. If I have a higher systolic pressure and a lower diastolic pressure, I'm going to have a higher pulse pressure, and there's more blood that's going to be ejected when the heart contracts. If I have a lower systolic pressure and a higher diastolic pressure, there's going to be less blood. And that's why the pulse pressure is going to be proportional to the stroke volume. When the pulse pressure goes up, the stroke volume is going to go up. Now, what's something that can narrow the pulse pressure? So in other words, if I say there's a narrow pulse pressure, these two values are going to be closer to each other. Okay, so like a narrow pulse pressure would be like 120 over 100. Okay, that would be a very narrow pulse pressure. Something like cardiac tamponade would be very classic for this. And there's a few conditions that can cause this, but remember with tamponade, we have an equilibration of pressure among a lot of the chambers because of the pressure from the pericardial effusion that's pushing down on the heart. Okay, so that would cause a narrow pulse pressure. A wide pulse pressure is if the pulse pressure is very high. Okay, so the classic thing that does this, probably the highest yield thing that does this, is going to be aortic regurgitation. The idea here is, if this is my left ventricle, okay, and then here's my aorta, blood ejected from here. If I have aortic regurgitation, some of that blood is actually going to come back. So I'm going to need a really strong force when I contract the left ventricle because I have so much blood coming back to it. I have blood coming into the left ventricle from the left atrium and backwards from the aorta. So I have blood coming back in two different directions to the left ventricle. Okay, so that's going to definitely increase the N diastolic volume here in the left ventricle. That's definitely going to have more sarcomere lengthening, higher levels of contractility, higher systolic pressures, right? So that's this part of the equation. And I'm also going to have lower diastolic pressures because the blood that's going to the aorta, a lot of it is going to be coming back if it's a severe aortic regurgitation. Okay, so the diastolic pressures are going to go down. So the diastolic pressures are going to be down, systolic pressures are going to be up. That's going to cause a higher pulse pressure. So, that's the classic condition I would remember for a widened pulse pressure is going to be aortic regurgitation. And then this last equation, again, is just really moving the numbers around, right? So if it just takes systolic blood pressure minus diastolic blood pressure, okay, plus diastolic blood pressure, and this is multiplied by 1/3. What I end up with is 1/3 systolic blood pressure minus 1/3 diastolic blood pressure plus diastolic blood pressure, and you'll see that this ends up becoming 2/3 diastolic blood pressure plus 1/3 systolic blood pressure. And that is the same equation as we had here. So again, a lot of this is just rearranging the equations, okay?